Hello, welcome to video 5. I'm Kunal. This is the longest and most content dense video in our series. We are covering exam section 3, model development. This section tests your understanding of algorithm selection, handling imbalance data, building training pipelines, hyperparameter tuning, cross validation, and evaluation metrics. We have a lot to cover, so let's jump right in. We'll start with selecting the right algorithm and handling imbalanced datasets. So let's talk about selecting the right algorithm. The exam expects you to match algorithm to the problem type. For classification, predicting categories like spam versus not spam, your options include logistic regression, random forest, XGBoost, and support vector machines. For regression, where you have to predict continuous values like house prices, use linear regression, random forest, or gradient boosting. For clustering, where you have to find groupings in unlabeled data, consider using k-means, dbScan, or hierarchical clustering. When choosing between algorithms, consider the data size, your interpretability requirements, the feature types, and the training time budget. So what is a good rule of thumb, right? So linear models handle high dimensionality data very well and are easily interpretable. Tree-based models handle nonlinear relationships and feature interactions without explicit engineering. Start simple, logistic or linear regression, then add complexity only if needed. The exam values this pragmatic approach. Now let's talk about mitigating the data imbalance. This is actually a direct exam question. The sample question describes a churn prediction scenario where only 10% of customers churn, which means a classic imbalanced dataset. The question asks which strategy directly mitigates the bias towards a majority class. Let me walk through the options the exam presents: oversampling duplicates or synthetically generate minority class samples, SMOT, synthetic minority oversampling technique. This is the most common approach. Undersampling, which reduces the majority class to create the balance. Cost-sensitive learnings assigned higher misclassification penalty to the minority class during the training. This actually directly tells the model getting the minority class wrong is more expensive than getting the majority class wrong. You can also use class weights. For example, class weight equals balanced in scikit-learn. The correct answer on the exam is cost-sensitive learning, not normalization that doesn't address imbalance, not collecting more data on the majority class that makes the problem worse, not using a simpler model that doesn't address the root cause. So remember, for imbalanced datasets, don't use accuracy as your metric. Always use F1 score, precision recall curves, or AUC instead. Now let's cover training pipelines and the three main approaches to hyperparameter tuning. Let's start with estimators versus transformers in Spark ML. In Spark ML, there are two fundamental abstractions you need to understand. Transformers take data frame as an input and produce data frame as output. They apply a fixed transformation. No learning is involved. Examples include a fitted one-hot encoder model, vector assembler, which combines columns, and a tokenizer, which actually splits the text. You call transform on your data frame and you to apply this. Estimators, on the other hand, take a data frame as input and produce a model, which is itself a transformer. Estimators learn from the data via the dot fit method. Examples include logistic regression, random forest classifier, and string indexer. When you call the dot fit method, the estimator learns from the data and returns a fitted model that you can then use to transform the new data. So what is the key insight? The string indexer is an estimator because it needs to learn the mappings of strings to indices. But the fitted string indexer model is a transformer because it actually applies that known mapping to the new data. You chain estimators and transformers together in a pipeline. The pipeline itself is an estimator when you call the dot fit method on it. What it does, it actually fits each estimator in sequence using the output of each step as an input to the next one. The result is a pipeline model, which is a transformer. The exam actually tests this distinction. Know which classes are estimators and which are the transformers. Now let's talk about hyperparameter tuning methods. There are 3 tuning methods for the exam. Grid search, that tries every possible combination of hyperparameters. Let's say if you have 3 values of C, 2 options for kernel, and 3 values for gamma, that's 3 times 2 times 3 equals 18 combinations. It's exhaustive and it's guaranteed to find the best combination in the grid, but it's very slow. Random search samples random combinations from the search space. It is faster than grid search and often finds comparable results because not all hyperparameters are equally important. Bayesian optimization implemented in Databricks through Hyperopt is the smartest approach. It learns from previous trials to intelligently choose the next set of hyperparameters to try out. The key function is fmin. You pass it an objective function, a search space, and the algorithm. For example, use tp.suggest for tree of Parson estimators and the max evals for the number of trials. To parallelize single node models for hyperparameter tuning on a Spark cluster, use Spark trials. This distributes different hyperparameter combinations across your cluster workers. Each worker trains a model with different hyperparameters simultaneously. On the exam, know the fmin syntax and understand that Spark trials enables parallel tuning. This is a direct exam question. Let me walk through the exact calculation. The sample question says you are tuning a SVM with grid search CV using 5-fold cross validation. The parameter grid has C with values 0.1, 1, and 10. That's 3 values. Kernel with 2 values. And gamma again with 3 values like 0.01, 0.1, and 1. Step 1, calculate all the grid search combinations. Multiply all the values. 3 times 2 times 3, which equals 18 unique combinations. Step 2, multiply by the number of cross-validation folds. Each combination is trained 5 times, once for each fold. So 18 times 5 is equal to 90 total models. So the answer is 90 models. The exam presents 90, 18, and 1, and none of the above. Choose 90. This calculation is straightforward, but it's easy to get wrong if you forget to multiply by the cross-validation folds. Total models equals grid combinations times k folds. Memorize this formula. Again, total models equals grid combinations times k folds. Now let's cover cross-validation and evaluation metrics you need for the exam. Cross-validation and train validation split are 2 approaches to estimating model performance. Cross-validation divides your data into k folds. In each iteration, k-1 folds are used for training and the remaining 1 fold is used for validation. Every data point gets used for both training and validation across the full process. So what are the benefits? More reliable performance estimates with lower variance and all the data is used. What is the downside? It's computationally expensive. You train k times as many models, right? So it's computationally expensive. A train validation split just divides data once, typically 80-20. Benefits, it's fast, simple. What are the downsides? High variance in the estimate because it depends on which data ends up in which split. You might meet some patterns that happen to land entirely in the held out dataset. The exam asks you to compare and contrast these. Cross-validation is better for small datasets where every data point matters. Train validation split is sufficient for large datasets where a single split is representative. Cross-validation is also used as a part of model fitting, for example, in cross-val score in scikit-learn or cross-validator in Spark ML. Now let's talk about classification versus regression metrics. This is dense but critical. The exam expects you to choose the right metric for a scenario. Let's start with classification metrics. F1 score is the harmonic mean of precision and recall. Use it for imbalanced datasets where you need both precision and recall to be decent. Log loss penalizes confident ROC predictions. It's good for evaluating probability outputs, not just the class predictions. ROCAOC measures performance across all classification thresholds. Use it when you want a threshold independent metric. Accuracy is simple and intuitive, but only useful when classes are balanced. They were used for imbalanced data. Precision is the right metric when false positives are costly. For example, spam detection, where you don't want legitimate emails marked as spam. Recall is right when false negatives are costly. For example, cancer detection when missing a positive case can be very dangerous. Now, moving on to regression metrics, RMSE or root mean squared error. It penalizes large errors more heavily because of the squaring part. It's the most common default metric used. Another metric is ME, which is mean absolute error. It is the average of all the absolute errors and is more robust to outliers because it doesn't square up. R squared represents the portion of variance explained ranging from 0 to 1. It's intuitive but can be misleading with non-linear relationships. Remember, R squared can be intuitive, but it could mislead if you have non-linear relationships in your data. On the exam, they will describe your scenario and ask you which metric is most appropriate. Match the business objective to the metric characteristics and you are done. Now let's talk about bias-variance trade-off and model complexity. The bias-variance trade-off is a fundamental ML concept and it is very important. High bias means underfitting. The model is too simple to capture the patterns in the data. It performs poorly on both training as well as the test dataset. High variance on the other side means overfitting. The model memorizes your training data very well, including the noise. It performs really well on the training data, but fails on the new data. As you increase the model complexity, like you add more features, you build deeper trees, more parameters, you reduce the bias, but you increase the variance. You need to find the optimal values where total error is minimized. So regularization techniques like L1, lasso, and L2 reach help reduce variance by constraining model complexity. They add a penalty term that actually discourages overly complex models. Cross-validation is also your base tool for detecting overfitting. If training performance is great, but cross-validation performance is poor, that means you are overfitting. Now let's talk about key takeaways from this section. Basically, model development essentials. Cost-sensitive learning directly addresses the class imbalance. Grid search combinations times CV folds equals total models. Remember, 18 times 5 equals 90, the sample exam question. Use Hyperopt's F-mean with Spark trials, which enables parallel Bayesian tuning on a Spark cluster. Use F1 score or AUC for imbalanced classification and use RMSE or ME for regression. One more time, exponentiate predictions from log transformed targets before computing metrics. Well, that was a big one. You have now covered the full model development section. Our final video, video 6, which covers model deployment. In that, we will look at batch, streaming, and real-time serving approaches, including the critical distinction between delta live tables and model serving endpoints. We are almost there. See you in the last video of this series. Thank you.